Okay, so hi again, everyone, and this is the second lecture tonight, and it's the last lecture of the series, and it's on algorithmic bias. So this is something that people have been aware of for a long time, but it's really starting to come to the fore. And what we find is that human bias is getting into our algorithms, and therefore, people who are discriminated against by humans, they seem to be also discriminated against by algorithms, and it seems to be the same sort of people that are discriminated against in both cases. And what's more, when it gets into an algorithm, it can really be amplified. So we need to make sure that that doesn't happen. It is going to happen, okay, but we need to put everything in place to try and make sure it doesn't, to be aware of it. So tonight, all I'm going to do is I'm going to make you aware of it. I'm going to give you some suggestions of things that you can do to try and mitigate it, but you can expect this to be something that's going to unfold much more over the years. As I was researching this, I found in many cases that you were coming back to the same small few people that were seen to be the experts in this area. There's a lot of talk about it, but not necessarily a lot of answers just yet as to how best to solve this. So the best practice is probably still to come. So this is something you need to kind of keep an eye on, something you need to be aware of. So bias by proxy. So the loss function that we've talked about quite a bit in machine learning and in deep learning, this is a proxy for what we really want to achieve, because in many cases we can't measure what we actually want to measure, because there's maybe no way of doing it. So for a loss function to work, it needs to be something that we can actually write into computer code. It needs to be tractable to calculate. So we can't be something that would take us, a year to calculate in a single instance. It has to be something that can be calculated relatively quickly, or otherwise it's not useful. And the third thing is it has to be differentiable. Okay, so we have to be able to get at least the finite difference of it, so that we can use it to calculate the back propagation algorithm and update our weights. So if it happens to be something that isn't one of these three, then we're going to have to use something else that we use as a proxy for us. In other words, that's in place of what we're really trying to measure, so that it gives us an idea of where we're going. Now, the problem is that the difference between the reality and the proxy can be all in the one direction, and therefore it can give a bias. So if we contain a bias in either like our objective function or our loss function, then we introduce that as an inherent bias into the model that we're creating. So take, for example, a system that wants to allocate resources in a hospital in the most beneficial manner to the community. Greatest need is hard to quantify. Okay, so let's use a proxy instead. So who has already used the resources the most? They are likely to be the people who will need the most care. Again, difficult to say who has used it the most, because what does that mean? Does that mean most hospital visits? Does it mean number of minutes that they were in the hospital, or number of hours? Does it mean the cost of what they were using? Were they using MRI scanners and so on? And in fact, in the link we have down there below about the hospital algorithms are biased against black patients, in that example, they were actually using as a proxy for the greatest need who had spent the most money in the hospital. Okay, so who had spent the most money on healthcare? And who spends the most money on healthcare? Rich people do. Invariably, they're rich white people. Particularly in the jurisdiction that this was in, they have the best health insurance, and therefore they have the most money that they can spend. And if you then decide, well, they're the people that need the most healthcare, well, what they found was that actually for the exact same condition, they found that the rich, well, just the white patients alone had greater access to that than the black patients. Okay, so we see this exact same situation again, whereby the people who are discriminated against by humans are also discriminated against by algorithms, because of course the algorithms are created by the humans, and humans make mistakes when they're doing it. Now, it's probably a little bit easier to solve the algorithmic bias when you spot it than it is maybe to change human behavior. But nonetheless, it's still a thorny problem that's not always that easy to solve. And we're going to see other ones here which are because maybe you can't come up with a better proxy, and that can be difficult. So if you consider something like an autonomous ambulance that's going to bring paramedics to the scene of to a scene where somebody needs help, what happens with that? What sort of decisions does it make? And it might decide, well, I'm going to make the decision on what's the easiest to get to, or how which ones have we successfully got to in a certain amount of time. And what you're going to find is that the rich areas are easier to access than the poor areas. They're probably even closer to a hospital. And therefore, you can see a situation where, once again, you're going to have a bias towards rich people rather than poor people. More examples of bias by proxy, and actually, I mentioned some of the that there were particular people that were doing a lot of work. Rachel Thomas here does a lot of work, and if you follow her on Twitter, she tweets a lot about different examples of bias. So she's very much worth following from that point of view. Rachel is one of the two people involved in the fast.ai course. And so she's somebody that's well worth keeping an eye on from that point of view. So you want to know what content users like, so you measure what they click on. And of course, the problem is there that they click on what's made available to them, not necessarily what they like. They may not have seen what they like. You want to know which teachers are most effective, so you measure their students' test scores. Now, test scores again are only a proxy for assessing learning, but measuring how effective a teacher is by that further proxy, that can be problematic. So you can imagine the situation of what's going to happen there. If let's say teachers were going to get performance pay based on their test scores, well, they can quite easily get those test scores up. That doesn't say that the student is learning more. They might be doing some sort of other things that they shouldn't be doing in order to make sure that those test scores go up. You want to know about a crime, so you measure arrests. But arrests just tell you who you're arresting. They don't tell you where the crime is. And of course, if the arrests are being made in a biased manner by humans, then you're immediately going to include that in. And we've seen that this has already happened. So particular areas are targeted simply because they're the areas that have had the most arrests in the past, and this goes on. You want to know what makes an effective employee, so you measure the attributes of your current employees. But that assumes that your current employees are the ones that are good, and therefore if they're already good, why are you measuring them? So you can see again that doesn't necessarily answer the question. So Rachel here makes the argument that these are poor proxies. Now, one particularly ironic example of where bias has got into a system is the Canadian immigration system. So Canada set about becoming a world leader in AI. Now, to some extent, I think this kind of happened after they were already a world leader in AI. So some of the top universities in Toronto and Montreal in particular had very good departments that were dealing with deep learning. That's where a lot of the modern deep learning ideas came out of. Jeffrey Hinton and people like that. And because of that, the Canadian government decided that they were going to obviously put a lot of resources into trying to become better at this and to keep a lead. Now, the NeurIPS conference has been held in Canada for the past 2 years, kind of based on this. And many of the top researchers in the world, including experts in bias in AI, which we're discussing now, they had their visa applications to attend the conference rejected, simply because they had African names, or they came from an African country, or maybe it was a country which you might associate with terrorism or something like that. Okay, now I think in most of the cases they were actually just coming from countries in which the system made the assumption that these were people who were likely to overstay their visa term. So ironically, in many cases, this is because their application was reviewed by an automated system that simply made a determination on their name, some of their details about them, and the country they were coming from. And of course, the point is that if you get your visa application and a lot of these are rejected, then you're going to have people at an AI conference asking questions about how exactly that was assessed. And when they find out that it was an algorithm that does it, they're going to be able to tear that algorithm apart. But imagine that you're just an ordinary citizen who knows nothing about AI, and all you get back is a rejection, and you don't know why you've been rejected. Okay. So the University of Toronto report finds that the use of automated decision-making technologies to augment or replace human judgment therefore threatens to violate domestic and international human rights law in Canadian immigration. Okay, so it's particularly ironic in their particular case. And this happens in all sorts of things. It's, you have automated systems being used to decide whether a convicted felon is likely to reoffend. So whether to give parole to somebody. And it's also been used in many systems which are recruiting people for jobs. And these have been tested reasonably robustly, where people have tested by putting in the exact same application, but put a name that would be associated with a black person and a name that would be associated with a white person, and huge discrepancies between who gets called for interview and who doesn't. Okay, so and that happens obviously with humans, and therefore it also happens with the systems that humans develop, and this has been shown in quite a number of ones. And one of the biggest problems that we currently face with regard to AI that can lead to these issues is that we treat dynamic problems as though they were static problems. So we assume that the current state of play is the state of play, and what we do is we use some form of like stochastic gradient descent in order to try and optimize that particular problem. What we don't realize is that we're trying to optimize a problem that's non-stationary, it's moving. And the other point about that movement is that it might be moving in response to our moves. Okay, so by our gradient descent moves, we may actually be changing the system in a dynamic way. Now, these systems, there are lots of dynamic systems, and we're only so at them. Generative adversarial networks are a typical example in which we know that they're not trying to optimize some stationary objective. They're trying to optimize what's called a Nash equilibrium. I won't go into the details on that, but if you're familiar with the film A Beautiful Mind, that was John Nash, and that was the idea he came up with, that there's this idea of gameplay and so on. But those are dynamic systems, and if we treat them as static systems, that they don't change over time when they actually do, and that they change in response to whatever decisions we make, then we end up making the situation worse in most cases. So we try to reach some objective without taking into account that the objective changes over time. Worse still, it may change in response to our actions to reach the objective. So take our first example that we had earlier. We want to give care to those that use the hospital the most. So what do? We look at who's used the hospital the most the previous time. We give them more healthcare, and the next time we measure, they're the ones that had the most healthcare, and we just compound the problem. So who do you think will be in that category next time we measure? Of course, the exact same people, and it will just create a kind of a self-fulfilling prophecy. Okay. And again, with some of the other examples we have there, if you use what viewers click on as a proxy for what they want, you will find that their choice of what to click on is narrowed and narrowed and narrowed to what they have clicked on previously. And they might have clicked on it and decided that they didn't like it, but that once they've clicked on it, you've taken it that they liked it. The example I gave earlier, as a teacher, if I'm assessed on test scores of my students and I set the exam, and I'm the one that tells people, that gives the lectures, and I'm the one that assesses it, then what do you think will happen test scores if that's related to my pay? Okay, so if I'm going to be assessed purely on my test scores instead of some other criteria, I'm not sure that I'm assessed on too much at all, but that's neither here nor there. You can see the sort of thing that would happen. If crime is measured by arrests, we'll target areas where most of the arrests took place. So you have particular locations within a city, and most of the arrests took place there, but you don't know that most of the arrests didn't take place there because of racial issues or any other sort of issues that might, for reasons why they might have occurred. It might be just easier to arrest people there than it is in some other areas that might have, poorer access to lawyers and so on. So what will happen? Well, those will continue to be the areas which have the highest arrest rates. So when you look next time to see where's the highest crime rate, you use the same proxy again, and you find that there was more arrests in this area, and therefore that's where you're going to put all your resources again. So you see these kind of self-fulfilling prophecy, and this is where these systems can amplify the problems caused by humans. Now, I mentioned data by proxy, but actually the far greater and much more difficult one to solve is when bias is in the data set. Okay, so the data itself has a bias, and therefore it's going to get into the model because the model learns from the data. So remember that the training data set is meant to be representative of the data generation distribution. So let's, and the problem is that if it isn't, and it's non-representative in that it's biased, okay? And if you remember the example that we had for when we were looking at batch normalization, we kind of had data that was in this range, and then we took a batch, and the batch was kind of in this range. That would be biased because it's not really covering the full range there. So you can see the sort of problems, and that's what's likely to happen if your data doesn't properly cover the full data generating distribution. So let's take, you're trying to train some natural language model. Now, NLP is not really my area, but let's take it as an example. You're trying to train it to be able to parse sentences for meaning, and a typical way to start is to use the vast corpus of books that we have that have been written over the past few centuries. This can seem a reasonable thing to do because if you use a huge set of books, then surely there could be no bias. Okay, and unfortunately that's not the case. Let's take a look at this graph here. Now, this I've credited there unknown, by the way. That has a link to where I've got the information from. It's just that it had written that the author was unknown, which gives me slight cause for concern, but because we don't know that it's been peer reviewed or otherwise. But if you look at this data here, this shows the percentage of books written by women in the open library or internet archive. Now, basically what this is that books that were digitized and just put up for free in the open library on the web, they were parsed for who, was the author male or female. Now, you might wonder why the results after 1922 are less meaningful rather than before 1922 being less meaningful. And the reason for that is that books after 1922 were subject to much more stringent copyright laws than books before 1922, and therefore we have much less confidence in all of those books being up on the open library. In fact, most of them aren't. Therefore, we don't know that we've got a representative sample. But before 1922, we have a pretty good representative sample, and you can see here that for most of this, we have a situation where, from about 1700 up to 1922, that less than 10% of books were written by women, and therefore, if that's the case, we cannot assume that these books did not have a bias towards men. Secondly, of course, they're books written in English, and the books written in English before 1922, the chances are those were white men that were writing those, and not black men, okay, or any other ethnic group, which of course in most cases would have been speaking another language. So if that's what you're using for your model, you can assume that that is going to have significant historical bias in it. Ben Blatt, again, this is not a peer-reviewed source, but it was an interesting book. So I've pulled out a few of the interesting things from it. I haven't read this book again, and I'm looking at somebody else's analysis of it here. Authors who are women write equally about men and women. Okay, and this was found from parsing the text in the book. But men write overwhelmingly about men. Okay, so if you have a situation where even you have 50% male and female authors, the chances are you're still going to have bias where there's more writing about men than about women. For every appearance of the word she in the classics by male authors, Blatt found 3 uses of the word he. Now, remember that deep learning and machine learning, these are fancy names for what are really statistical machines. And statistical machines look for more data on one thing than another, and what they're going to assume is that he is 75% prevalent and she is only 25% prevalent, and that's just with the male authors. In classics by women, the ratio is pretty much 1-to-1. Okay, what it is after that we don't know, but of course only about 10% of the classics are actually written by women. There's one extreme example here, which is The Hobbit, which I'm sure many of you have read. It has, I couldn't get the correct figure. I did hear it at some point, but in a podcast, but I've lost the information. And it was a podcast about this particular book. 1900 over 1900 references to the word he, and only one mention of the word she. So that's a very extreme example there. This diagram over here is a kind of an interesting one where Ben Blatt did some analysis of the word interrupted and looked at the personal pronoun that was used before the word interrupted when you were looking at male authors and female authors. So what we're basically saying is here, when did the text come along that says he interrupted or she interrupted? And what he found was that with male authors, the ratio was that, you know, about 3 to 1, she interrupted rather than he interrupted. Okay, in other words, the assumption that women interrupt more often than men, that's what a statistical machine is going to pull from that. Now, the female author, it was the opposite way around. It was almost a 2 to 1 that men interrupted more than women interrupted, if we were to assume that. Not quite as high as what it was in the males, but you can see there where biases creep into this in the way people write. And therefore, it's going to be difficult to try and not have that bias get into your model. So you need to be aware of it. What about bias in image data sets, which is the one we're probably more interested in? So we face much the same problem here. Much of the research is done on open data sets because, of course, data sets that are proprietary are not as easy for university researchers to work on, and that's where a lot of the moves forward happen. If private companies do them, but we can't actually work on their data set, then that becomes less useful to us, and it certainly doesn't, get out towards to the entire community. If we take things like transfer learning, where we don't even train on the data, but that the model that we're using was already trained on some open data set like ImageNet, then the entire point of the model is to internalize the statistics of that data. So it will have internalized any bias that is in there. Okay, that's not just an accident, that's its job to do that. If there is a bias in there, it has to go and find it. And indeed, we use that term bias is not always a bad thing. You've seen there where we were looking at neural nets and we had that bias element that was in there. That is for that reason. It's to give you offsets that are actually in the data. It's to actually find that information. That's useful in most cases. That's almost like a very obvious intuition. If it has 4 legs and it barks, then it's probably a dog. Okay, but the problem is that if we have biases in there that are not representative of the data generation distribution. So in other words, are not representative of all the sort of people that we need to be for it to be representative of, then it is going to learn that bias. So ImageNet is perhaps the best known of the open image datasets, with just over 14 million images. Now, you might think 14 million images is a huge amount of images, but when you consider all of the natural images in the world, right? Firstly, that's an awful lot of photographs. It's many times 14 million. So 14 million is never going to cover all of the natural images that have been taken in the world. Secondly, where are the natural images more often taken? Okay, so who has cameras? Well, certainly people in developing world who cannot afford a bicycle and are subsiding on $2 a day, they're very unlikely to have a camera or to use it. So we're not seeing that to the same extent that we're going to see images generated. Even if they do take images, the chances that they have internet access and those are going up in places where we're going to have access to those to use them in data sets, much more unlikely. So we've all sorts of issues with these open data sets because they overwhelmingly represent Western countries that have, that are basically well off of the top OECD countries. So is this biased? Well, while 40 million is a lot, to assume that it can cover the distribution of natural images is a completely naive standpoint. And some analysis has been done of this. There's a good paper by Shrina Shankar called No Classification Without Representation. And this investigates the geodiversity of ImageNet. On the next slide, we see an investigation that I think it's a she, I'm not sure, but that she did into the investigation of open images, the open images dataset, which is another very large dataset that people use. The main conclusion from their tests was that you couldn't expect to classify people in the developing world if trained on these data sets. Okay, so let's have a look at the ImageNet here. You can see that 45.4% of the data is from the US, 7.6% from Great Britain. You've got Italy, Canada, Australia, Spain, Argentina, Ireland got in there, and I think this is the Caicos Islands. I'm not sure why they picked that particular one, but that's probably one of the smaller of them there. So you can see there's a lot of other countries represented here, but overwhelmingly, this is split into, the US and Great Britain alone make over 50% of it, and these are all, white, Caucasian, wealthy nations. That are covered by ImageNet, and therefore a lot of what we're trained on. Something that I forgot to do and I meant to do was to show you, if you remember when we were going through some of the popular networks, we looked at the number of citations that papers got. I think this paper, when I looked at it, it had about 15, 16 citations. When you compare that to 20,000 citations and 30,000 and 40,000 citations, you can see how, as important as this research is, it's not getting anywhere near the sort of traction that is required for us to really get a grip on how big of an issue this bias is. And if we're not seeing that, and we're not seeing people quoting it in the work, it means that people are working on the algorithms. They're not stopping and thinking about the biases that are in there, and that's something we need to do more and more. The second one is on the open images, and this is where they look at the geographically where the open images were taken. Now, one of the problems with ImageNet was that they're not absolutely certain where each of the different images were taken, whereas I think they have a little bit more information in the EXIF data from open images as to where they were taken. So you can see here that the darker the region, the more represented that it is, and you can see huge regions here in Africa and so on, and up into these countries here, which just get no representation at all, and huge representation in the US, the UK, and so on. So exact same sort of thing happening. So what about bias in autonomous vehicles? How might an autonomous vehicle be biased, and particularly with human bias? So there's a major failure with autonomous vehicles to detect dark-skinned pedestrians. So once again, we have the exact same people being prejudiced against by accident, obviously in this case, but nonetheless, the problem still exists. So Benjamin Wilson et al. Looked at this in a paper called Predictive Inequity in Object Detection. So they divided up the people using a thing called the Fitzpatrick scale, which I wasn't aware existed, but it's a scale that classifies human skin tones from light to dark. And they found, Wilson et al., they found that detection was 5 percentage points, so not 5% in overall, but 5 percentage points, which is even worse, less accurate on average for dark-skinned groups when controlled for all the other variables like lighting and so on. Okay, so for all the other issues, they were able to control for all that and just look at what the difference was in the circumstances, and dark-skinned groups were that bit harder to classify accurately. Okay, so if you now have autonomous vehicles where the accident rate is going to be higher, where it's knocking down more people of a particular skin color than others, then we've got a serious problem on our hands. That even if fewer people are harmed by cars by going to autonomous vehicles, if we introduce this unfairness into the system, that's something that's just not palatable, and that we really need to make efforts to try and solve. And of course, this is a technical issue. It's partly that this might be in the data set. It's partly that dark-skinned pedestrians are going to be that little bit harder to see because of the light levels that are coming from them. But that's just tough. We've got to deal with that. We have to make sure that our algorithms are as fair as possible in terms of trying to cater for every sort of different possibility. The Uber crash, which I think Shane covered, which he in quite a bit of detail. I know for the guys who were there last year, I remember I think he gave a lecture on it, and maybe he's covered it again this year for you this year, or maybe he's changed it a little bit. But 49-year-old Elaine Hertzberg was killed when an autonomous vehicle hit her in March 2018. Did bias play a role here? Now, I don't as far as I know, gender and race were not an issue here for this system. I think she was a white Caucasian, so I don't think there was any clear, obvious bias from that point of view that was in the system. It's not to say, by the way, that the system couldn't end up being biased against white people or that, but because that certainly could happen, but it's just far less likely. This system did see her in plenty of time to stop. Okay, so it first recorded that it had spotted her 5.6 seconds before she was knocked down. Now that is plenty of time. I think the vehicle was going somewhere in the 40 to 50 either mile per hour or kilometre per hour. It's in the US, so it might be miles per hour, but I remember seeing a number in the 40s. But that's still enough. You have enough time to get the vehicle stopped, or at least to seriously mitigate the accident. Where as it was, it didn't press the brakes, I think, until after it had hit her. The problem was that it didn't recognise her as a pedestrian because she was not where pedestrians are supposed to be. Okay, so in other words, if you see somebody and they're on a crosswalk or on the footpath, as we call it, or as the Americans call it, the sidewalk, and the crosswalk, as we call it, a zebra crossing, then that's obviously pedestrian. But if they're in some other part of the road, they must be something else. Okay, and as we know, lots of people cross the road at all sorts of unusual intersections. And I think in this particular case, it was an obvious place to cross if you were a pedestrian because you were coming out from some sort of place. And that's what pedestrians tend to do. They're outside in the elements. They tend to take the shortest route, even if they're fairly law abiding other than that. Hertzberg was jaywalking. So she was breaking the law, strictly speaking. And the system never trained for this. So it was biased towards assuming that humans always follow the rules. That's very naive. And don't make mistakes. That's even more naive because humans pretty much defined by making mistakes. Okay, so imagine a human driver that sees the pedestrian in time, but because the pedestrian is not obeying the rules of the road, makes no attempt to stop. Clearly, that driver is not going to have their license very much longer. You just can't allow people out on the road who take that attitude. It doesn't matter that if the more vulnerable road user is breaking the law, you still have to take account of that. Vehicles have to do that too, but in this case, the vehicle didn't recognise that it was a pedestrian simply because the pedestrian was breaking the law. So, despite our best efforts, we ourselves, when we build algorithms, are biased towards assuming the best case scenario rather than the worst case scenario. We all the time talk about these different worst, but what we do is we go for the obvious one. So we assume if we're making at our first attempt at making an autonomous vehicle, we're going to assume that everybody is obeying the law and we're not going to be taken into account. And the reason for that is that there are far fewer situations to take account of there than all of the situations in which somebody could go outside of the law, either by mistake or on purpose. And whether the law that they're breaking is serious or relatively minor, and I would put jaywalking into the relatively minor one here. Of course, it resulted in this lady losing her life. But I don't think it's a simple matter to simply put the blame on her to say that she was jaywalking and therefore she was responsible. It's clearly got to be a little bit more nuanced than that. Okay, so this is a slide on types of bias by these guys. It's from a paper called A Framework for Understanding Unintended Consequences of Machine Learning by Hirani Suresh and John V. Gutenberg. And they look at the different types of bias and how that might get into a system. So we start with historical bias, which is like the example that I showed you earlier with if we take all the books and the books are predominantly written by white men, and they're written about men, then we're going to have bias getting into it in that way. If we take something like the ImageNet situation, we can see that we've taken images that are predominantly from the US and the UK and other first world nations, which are predominantly white Caucasian. And that's then our population that we're going to draw from. And from that, we then draw a sample, which are 14 million images, and that's meant to be representative of this population here. But it's not. It won't probably be perfectly representative of it. It probably introduces a bias, and again, in turn, it's not necessarily representative of the entire world either. It's only representative of the population that we've chosen. that gets into our data set, and then along with our evaluation and our benchmarks that we're checking it against, we have all sorts of other problems that can get in. Now with data generation, then we have the different sort of, when we're developing the model, the different sort of things that we pull together, the aggregation bias, and then we have the evaluation bias as to how we evaluate it, be it the loss function or the objective or whatever. And when we run the model, then it creates results in the real world that have real world implications. And that then gets back into the system, that gets back into the problems that we have in terms of historical bias and so on. Because if we find that, let's say, for example, that in the past, these people were given longer jail terms, then they're going to get longer jail terms again, because it gets back into the data. So see, these are some of the types of bias. I'd like to spend a bit more time on this paper, but it's a useful one maybe to have a read on, to just consider all the different places that bias can get into the system. So simply trying to keep it out of our loss function or our data set, well, you can see we've all sorts of problems before we ever get to there at all. So how do we avoid, because it's very easy to just get into a situation where we just give you piles of examples of where this has gone wrong. And this is part of the problem with, I found when I was researching this, was that it was short enough on advice and more or less just in telling us that there are all sorts of problems. So particularly where you want to avoid bias when you're detecting humans. So one of the ones that's obviously going to be very important when it comes to autonomous vehicles. So you need to consider all of the following. And I'd say this is not an exhaustive list. There's probably other things that I haven't thought to put in here. This came from IBM, an IBM paper on mitigating bias. So you need to consider all the following. Is there a good balance of genders within the system to make sure that you are equally fair to both? What about skin type? Have you taken into account all the different colors of skin? What about hair color? So if somebody has different color hair, or maybe they've no hair, or they've got a head covering, will the system recognize them all equally? What about age? So we have obviously a big issue in that tech companies have almost a fetish for young employees who are energetic and who are mad to go creating these algorithms. And as well as that, an awful lot of the data that's been created is being created by the younger generations rather than the older generations. So therefore, are older people, and particularly the very elderly, are they underrepresented in these data sets? Because if they are, it's going to be much harder for the system to recognize them. What about different ethnicities, which is separate from obviously skin type? So this can be, that they have kind of different facial features, or different types of haircuts, different types of dress, and so on. Can it tell all of those people as being as being pedestrians or whatever that we might be trying to find? What about disability assistance? So if somebody's in a wheelchair, or maybe they're on crutches, or maybe they've got they're blind and they've got a stick, or they've got some other assistance there. Maybe they've got a dog with them. Can we spot those as being pedestrians? Are they well represented? So you can easily see a situation where it's going to be much harder to spot somebody in a wheelchair as being a pedestrian compared to standard pedestrians who move at a particular pace, move in a particular way. What about pose? Again, the elderly, they might be much more stooped. It might be not as obvious that they're a human if they're underrepresented in the data set. Are they wearing glasses? Is that going to be a problem? What about the illumination? So the illumination in the region, is it harder to see some of these different types of people under different lighting? Therefore, you need to test for all of those. What about resolution and scale? Is it more difficult to see certain people when they're further away, or is it more difficult to see children than it is to see adults? The expression that somebody's wearing. Now that's generally not going to be an issue, I think, for pedestrian detection, but for other types of detection, if somebody has an unusual expression, or we haven't taken into account all the different expressions that somebody might have, it might not be as quick to recognize them. Accessories like earphones and things like that. If you've got the big set of headphones on you, can they still tell you apart? Decoration, jewellery, tattoos, body piercings. You can particularly see the tattoos being an issue because it might actually see a picture in the tattoo and show that up as the object instead of the person. All sorts of hair accessories as well. People wear their hair in an awful lot of different ways, and you can see all the different things. So you can see that there's an awful lot to cover, and you've got to cover that all of those happen. In other words, that you've tested illumination for all of these different types of things. So you can see there that these are the sort of things you're going to have to keep into account if you're looking at bias. So avoiding bias in general then, make sure that the teams developing new technologies are racially, gender and age diverse. As I said, there has a tendency to be that it's a predominantly male profession. Okay, and that seems to have been that way for a number of decades. That's not going to bode well for women into the future if we're not hearing that point of view within teams. If we're not seeing all of the different races represented in teams, we're not going to know about the specifics of something that we might be biased towards them without, and most of these are unconscious biases. Age diverse, again, as I say, predominantly in tech, it tends to be younger people, and it's harder for older people to actually get jobs in this. That needs to change because people who are older, they're going to have more life experience. They may spot these sort of things easier, but they're also just representative of that age group. You need to see feedback from the intended users, and you need to constantly scan for sources of bias. Checklist here again. Have we tested our training data to ensure that it is fair and representative? Have we studied and understood possible sources of bias in our data? Does our team reflect diversity of opinions, backgrounds and kinds of thought? Okay. Have we tested for fairness with respect to different user groups? Okay. Have we tested for disparate error rates among different user groups? So if we look at male and female, for example, if we're not seeing the same sort of accuracies and error rates, if we test for different skin colors and we don't see the same sort of accuracy or error rates, we need to really look into that. Do we test and monitor for model drift to ensure that our software remains fair over time, that it doesn't maybe cause an unfairness or so on? So I'm going to end tonight, and I'm really ending the entire machine learning with this particular slide. It's just some advice with regard to this, because this goes for all of machine learning. Don't confuse confidence with competence. Okay, now that seems an obvious one, but this is both in yourself. A lot of computer science and electronic engineering, I see a lot of students who some will not have great confidence, but many others will be overconfident about their abilities because they seem to be able to do things that maybe other people aren't able to do with computers, and that puts it into their head that they're some sort of master of the universe. They're nothing of the sort, and you need to be very, very aware that of what your competence is and what the edges of that competence are. And this also goes for if you're interviewing people. You need to make sure that just because somebody comes across confidently, or maybe it's a client, or maybe it's somebody you're buying something from, just because they come across confidently does not necessarily mean they're competent. You need to drill down to find out what their competence is, and that means that if you don't have the competency to do that, you need to seek out somebody who will. Don't just assume that you can measure that. But particularly in yourself, don't assume you know how something works. Always go back to scientific principles. I've made the word work in bold here at the end because it's important. Constantly question your own work and your team's work. I don't mean constantly question people. I mean constantly question their work. And if you can instill that sort of environment, that sort of culture in your company where everybody looks at each other's work and tries to improve each other's work, then that removes the personal element from it. That's vitally important. So encourage others to question your work as well. If you're able to answer the question that they ask, there should be no problem. If you can't, then they've helped you identify a problem. So don't look at when somebody questions your work and what you're doing, don't look at that as a personal affront to you. This is about the work. Even if they make it personal, you can always look and say, is there something that I can benefit from that? And if you do, it'll make life a little bit easier on you. But it's very important in these systems. I've shown you how bias can get in. You're going to have your own biases. It's very important that you let other people question your work and what you're doing, because that's how it gets made stronger. I found it difficult to write this sentence for exactly how to word it, but what I'm getting at here with if you rely on claims of seniority, reputation, or superior knowledge to answer a question, then you haven't answered the question properly. And this is where you say, well, I'm the boss, you have to do what I say. That's not a good idea. You should be able to answer whatever question they are, no matter how if the person isn't as senior as you, or if you just have a reputation built up. Again, you should be able to answer the specific question that you were asked, not rely on the fact that you have 30 years experience in this and say, well, or I've won awards or I've done whatever. Likewise, if you have superior knowledge than the person who's asking the question, you should still be able to answer their question. And if you can't, you need to question yourself and say, well, okay, have I thought this fully through? Do I know how this works? And finally, just a bit of advice, use checklists wherever you can, because if you use a checklist, that stops you from deciding that you're not going to just thinking automatically that you've done something. So open cultures like these that question each other's work but don't have a blame culture, those cultures excel, and blame cultures generally fail. There's a very good book there, recommendation. I read it on Audible a few years ago, called Black Box Thinking, from Matthew Said, where he goes through this in different types of industries, and it's very worth reading. I'm conscious of the time, guys. I know you have another class in about 1 minute, and so do I. So firstly, just want to say thank you to you for all of your attention over the last semester. Hope the exams and everything goes well for you, and I'll say goodnight to you with that.